What if I told you that the next life-saving medicine could be discovered in a fraction of the time it takes today? It might sound like science fiction, but it's a revolution that's happening in chemistry labs right now. And we're going to break down exactly how it's changing, well, everything.
I mean, really think about that for a second. What if creating a brand new molecule, one that could be the key to curing a disease, took less time than getting takeout on a Friday night? It seems almost impossible, but that is exactly where we're heading.
All right, so to really get why this new technique is such a massive deal, we first have to look at the old way of doing things. I like to call it the chemist's slow cooker.
For decades, making molecules for medical research was, well, a lot like making a really complicated stew. You'd mix your ingredients, you'd heat them up super gently for hours and hours, and basically just keep your fingers crossed that something good would happen. It's an incredibly slow, often inefficient process that could burn through an entire day for just a single try.
So, what if we could just ditch that old slow cooker for, say, a super-powered high-tech microwave? Well, that brings us to the breakthrough at the heart of our story today, the microwave makeover.
This game-changing tech is called Microwave-assisted organic synthesis, or MOS for short. Now, just to be clear, this is not your kitchen microwave for reheating leftovers. No way. This is a highly specialized piece of lab equipment that uses focused energy to heat chemical reactions with just incredible speed and precision. It works by zapping the molecules directly all at once, which gives you this perfectly uniform heating.
And the benefits here are, well, they're huge. First off, as you can guess, the reactions are just ridiculously fast. But you also get more of the molecule you actually want to make, what scientists call a higher yield. The end product is cleaner, more pure, and on top of all that, it's a greener process that saves a ton of energy. It's a win-win-win.
So let's really see this in action. Let's put these two methods head-to-head to really appreciate how dramatic the difference is. It's old school versus the new wave.
Okay, the difference is truly night and day. On the left, you've got the traditional method. It's like the turtle in the race. It's slow, the heating is uneven because it comes from the outside in, and you just get less of what you want. But on the right, you have a rocket ship. The microwave method is blazing fast, the heating is perfectly even, and the results are just so much better. It's a total upgrade in every single way.
So, just how slow was the old way? A single reaction could easily take anywhere between 3 and 6 hours. That's pretty much half a workday gone for just one experiment.
Now, are you ready for this? Compare that to the new MAOS method. The exact same reaction, it's done in just 20 to 40 minutes. Think about that. We've gone from half a day's work down to the time it takes to watch a TV show. That is a monumental leap.
And here's the other crucial advantage, and this chart just says it all. It isn't just about speed, it's about getting more of what you need. This shows the yield, basically how much of the good stuff you get out of the reaction. And as you can see, the MAOS method often cranks out more than double the amount of the molecule you're trying to make. So you're working faster and getting way better results.
So, you might be wondering, what does this actually look like in the lab? Well, let's walk through what we can pretty much call the 20-minute recipe.
What's so amazing is just how simple this makes everything. You literally just combine your starting chemicals in a special vial. You pop it in the microwave reactor for about 20 minutes. Then, you pour the whole mixture over some ice, which makes your new molecule turn into a solid. A quick little filter and a wash, and boom, you have your pure, final product. It is an incredibly streamlined way to build something completely new from scratch.
So we've got a faster, cleaner, more efficient recipe. That's all great, but what's the real-world impact? This brings us to the most important part of the whole story, why this matters.
The connection here is simple, but it is so profound. When you can create new molecules this quickly, you can test more ideas, so many more. Researchers can run dozens of experiments in the time it used to take to run just one. This radically accelerates the entire pipeline of drug discovery, from an idea on a whiteboard to a potential life-saving treatment.
But of course, researchers aren't just in the lab making random molecules and hoping for the best. Nope. They're designing them with a very specific purpose. They use guides like Lipinski's Rule of 5. And don't worry about the fancy name. It's basically a checklist, a set of rules of thumb to predict if a new molecule has the right stuff to become an effective drug in the human body. This new speed lets them test only the most promising candidates that actually fit these rules.
And this right here is the ultimate goal, and this quote is straight from the source material. The whole point of this high-speed chemistry is to create these novel molecules that can then be explored for powerful biological activities, like fighting cancer. You see, this isn't just some clever trick to save time in the lab. It's a direct path toward developing the next generation of therapies.
So we'll leave you with this final thought. We've watched a chemical process go from taking hours and hours down to just a few minutes. The door is now blown wide open for faster discovery and more rapid innovation than we've ever seen before. It really makes you wonder, doesn't it? If we can now design and create the building blocks for new medicines this fast, what future cures are truly just around the corner?